Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. A chiral molecule is one that is non-superimposable on its mirror image. The most common source of chirality is a stereocenter, sp3 carbon bearing 4 different substituents. Moving on to the next step. The structure is CH3, CH2, CH3 is equal to CH, CH2, CH3. C3 is part of a double bond, sp2, trigonal planar, and therefore cannot be a stereocenter. No other sp3 carbon bears 4 different groups. Not chiral. Moving on to the next step. This is a cyclohexane ring with a methyl group at C1 and a chlorine at C4. C1 has methyl, H, and 2 ring carbons, C2 and C6. C4 has Cl, H, and 2 ring carbons, C3 and C5. In the parent numbering, C3 and C5 are equivalent, symmetric, and C2 and C6 are equivalent, symmetric, making both C1 and C4 not true stereocenters. They each have 2 identical substituents via the ring. The molecule has a plane of symmetry. Not chiral. And for the final step. The structure is C6H5CH, CH3, CH2, CH2, CH3. C2 bears a phenyl group, a methyl group, CH3, a hydrogen, H, and a propyl chain, CH to CH to CH3. All 4 substituents are different, making C2 a true stereocenter. This molecule is chiral. The benzene ring with 2 identical isopropyl groups at positions 1 and 3 has a plane of symmetry through the ring. The isopropyl groups themselves are CH, CH3, 2 where the central carbon bears 2 identical methyl groups, so no stereocenter exists. Not chiral. Conclusion: only 2-phenylpentane, option C, possesses a true stereocenter with 4 different substituents and no internal plane of symmetry, making it chiral. Therefore, the correct answer is C. Therefore, the correct answer is option C.